Good morning, afternoon, or evening, Dr. Kris and the teaching team, depending on when you're seeing this. The contents of this video detail the major cliff notes of our final project. As far as our team members go, we have myself, Aiden Kinnicut, we have Anton Kirichenko, we have Kris Ryan, Jack Purvis, and finally, Abby Street. As far as the project goes, the purpose of this was to close the gap between the knowledge that we've been taught in class and the physical aircrafts themselves. To accomplish these goals, we applied analytical tools and methods touched on throughout the course to physical KU aircraft like UAS, or in our case, aircraft number 4. So we constructed a complete aerodynamic and dynamic model of the aircraft. We used advanced aircraft analysis, AAA, and Athena Vortex Lattice, AVL, to estimate our aerodynamic coefficients, determine trim conditions at our case, which was 50 feet per second and 1,100 feet altitude, and perform sensitivity studies with respect to the aircraft geometry and center of gravity location. What we've done demonstrates how the theoretical concepts of stability analysis, trim, and dynamic modeling translate into practical engineering tools and real aircraft behavior. In doing so, it connects the mathematical framework of aircraft dynamics to the physical reality of operational UAS and develops familiarity with the software and modeling workflow used in professional aeronautical design and analysis. As for the aircraft, we were given, obviously, aircraft number 4, better known to us as the ASW-17 EP glider, which is commercially sold by FMS, a company that manufactures RC cars and planes. It's a small electric-powered sailplane kind of glider characterized by a high aspect ratio and low wing loading. The characteristics yield high motor efficiency, high soaring efficiency, and very low sneak rates, allowing for much better glide. It was constructed from EPO foam with an internal spar and metal wing joiner. The model exhibits stable longitudinal behavior, while lateral dynamics are marked by relatively low roll damping and modest roll authority control. To obtain our stability and control derivatives, we had to do a lot of analysis within AAA, and the first step into getting that model fully functional within AAA is to fully develop our geometry of the aircraft itself.
So the geometry of the aircraft is that of a conventional glider. It has the conventional glider main platforms, which are a wing, a horizontal tail, and a vertical tail, as seen in this 3 view. The wing is a mid-wing with a slight dihedral, but the important part is it follows conventional glider principles, where it's got a large aspect ratio to reduce drag. It also has 2 control surfaces, flaps and ailerons. Flaps are high lift devices used in takeoff and landing, and ailerons are roll control devices. Between the 2 control surfaces, almost the entire wingspan is taken up by control surfaces, flaps, and then outboard ailerons. The horizontal tail is mounted just like with the vertical tail, mounted at the end of the fuselage. The horizontal tail is mounted slightly above the fuselage on the vertical tail. It features an elevator that runs the entire span of the horizontal tail, and that's used for pitch control. The vertical tail is also, again, mounted at the end of the fuselage, and it also extends off of the end of the fuselage. It features a rudder with an unshielded rudder horn. What this means is, yes, the rudder spans the entire vertical tail, but also at the top, where the moment arm is greatest, the rudder doesn't just span the aft portion of the vertical tail, but the entire vertical tail to increase control. Now, the fuselage is a complex geometry. It is an aerodynamic teardrop shape with most of the mass and volume concentrated at the front and then tapering off sharply but smoothly to a boom-like shape, where at the end of which the vertical tail and the horizontal tail are mounted. It is a complex shape, so unlike the other geometries that can be rendered directly in AAA, this one first has to be CAD'd and then imported into AAA. Now, at the tip of the fuselage is mounted a propeller, a 2-blade propeller that's our propulsion system, and also at the bottom there is one singular wheel that is our landing gear to provide a safe spot to land so the fuselage does not get damaged during landing. After the geometry is rendered in AAA, combined with the flight condition, stability derivatives may be found.
So for the stability derivatives, we care about longitudinal stability and lateral directional stability. Now, these derivatives should cause restorative forces for small changes in airflow angles, alpha and beta. To have longitudinal stability, you care about a restorative force in your pitching moment, or restorative moment. So in that case, you want your CM alpha coefficient to be negative. That causes a restoring force by general convention. For the lateral and directional stability, you care about the rolling and the yawing moment, as well as the side force. Rolling moment and the side force coefficient stability derivatives, CL beta and CY beta, should both be negative, while the yawing moment coefficient, CN beta, should be positive. All of the stability derivatives that were calculated using each person's AAA models were within reason and contained the right signage to signify that everyone's models were aerodynamically stable. Now, on top of this, you also care about the responsiveness of your system, which is given by the static margin. For gliders and small UAVs, a static margin between 0 and 10% while still being positive is optimal. For gliders, the most optimal is about 3 to 5%. And as per our data, everyone got a positive within reason static margin, roughly around 7 and 5%, averaging around 6%. From this, we know that our aircraft is both aerodynamically stable and responsive.
In order to produce AAA models of our assigned aircraft, we first needed to take measurements of the geometry. Once measurements were taken, they were stored in an Excel file where other parameters such as C-bar and lambda were calculated. For any parameters that could not be measured or calculated, we made educated assumptions or tried finding resources online. For the fuselage section, we took precise images of the aircraft and CAD'd them in Siemens NX. With the CAD model of the fuselage, we could import it into AAA and incorporate it into our geometry. After inputting our flight parameters and values from the geometry spreadsheet, AAA generated a 3-view model of the aircraft. From here, group members individually performed aerodynamic analysis on their models, and since each member made their own assumptions for parameters such as airfoil type and drag component, each analysis was slightly different. For example, Kris included the landing gear in her drag analysis, whereas my model assumed the landing gear wheel had negligible effects on drag. Despite slight differences in each AAA model, we all got similar values as previously mentioned. Once each analysis was performed, all results including stability derivatives, CG locations, and moment of inertia estimates were exported as Excel files and consolidated into one Excel file. Once each analysis was performed, all results including stability derivatives, CG locations, and moments of inertia estimates were exported as Excel files and consolidated into one Excel file where they could now be compared. After comparison, group members began working on their individual report writing, followed by the group report writing sections.
So the major takeaways from this project were to analyze what we have been learning in class, like control derivatives and the stability of an aircraft with a real-life example. This project taught us a lot about AAA and how to use it to get control derivatives without having to manually do them all by hand, and so that was very helpful. It was a big learning experience and overall will be useful for future projects. Major differences between each of our models was the placement of the center of gravity. So for a UAV, we want our static margin to be between 0 and 10%. And so location of the center of gravity needs to be in a position that yields a static margin in that range. Our aircraft was stable, which is great. And how we determined this was our CM alpha, CY beta, and CL beta were all negative, and our CN beta was positive. These control derivatives are essential in determining whether or not our aircraft is stable or unstable, and of course we want a stable aircraft. And so we were looking to get these control derivatives and also a static margin between 0 and 10%, and we got that. And so I would say that this project was very successful. So one thing that could be different was lowering our static margin slightly. We don't want it too low especially we don't want it negative. If it's negative, that means we're receiving energy from our environment. So any major gust of wind, any high alphas, we will have loss of control. And so we want it to still be in the positive range, but lowering it slightly can yield a more responsive aircraft. And so one thing we could do would be change our center of gravity slightly more. I noticed that when I moved the CG back too far back though, it did yield a better static margin, but it required more surface deflection from some of our controls. And so we want to keep in mind that just because we have a lower static margin, it doesn't necessarily mean that's the best design. Our team would like to thank Dr. Kashmiri, Ashish, Joey, and Scott for all their help throughout the semester and giving us this opportunity to apply all our knowledge learned throughout the course to a real-world application.